So let's start reviewing the key properties or the key features that Dijkstra relies on in order to work. So we are going to be talking about these features as once we know a vertex, once we've marked it as known, we have now found its shortest path. And we can always reconstruct that path following those back pointers in our map. So we're saying our invariant here is every time we're adding something to the known set, there is no way to have a different, shorter path. Now, the kind of converse of that, like I mentioned before, was while we haven't added a vertex to our known set, there might be another shorter path. So we shouldn't make any statements quite yet. Now, one thing that's important to mention is that order added to the known set, that thing I was keeping track of during the kind of slides before, is actually unimportant. It's just a detail about how the algorithm works that the client doesn't care about. The client just cares about the final result. What is the shortest path? And it's not used by the algorithm. It's not assuming that the order that we explore those tie cases matters. So we're just going to always assume that it's sorted by the path distance, which is what we wanted, and the ties are resolved somehow. We don't care about the tie cases because ultimately it will end up with the same result. Now, one thing I should mention is that just like with unweighted shortest paths, if we only wanted to find the distance or the shortest path to our particular vertex, you could have stopped early. Once you know that vertex's shortest distance, you could just stop. But one thing that's pretty nice is knowing that whole shortest path tree, because then it lets you answer those questions for any node in the graph. Now, one thing I'm not going to walk through in this video is in the slides, I have a whole nother example of walking through Dijkstra's. You should definitely walk through that and make sure, I think is a good exercise, is trying to guess what the updates are at each step. Okay? That could be good practice before coming to class on Friday. But what I want to talk about in this video is why does Dijkstra's work? So Dijkstra's works because of this invariant that all vertices in the known set have the correct shortest path. It's very similar to our first try phenomenon for that breadth first search. It's saying that we know the shortest distance whenever we add something to our known set. Now, how do we make so it's nice that we can assume that a variant is true beforehand, but how do we make sure on each iteration of this algorithm that we're maintaining this invariant? And so my argument is this invariant is held by answering this question. How can we make sure that we won't find a shorter path to some node X later? So how can we be sure that we won't find the shortest path? So suppose, for example, I had this kind of algorithm in this state. I have this node B here, and it is currently in my known set. So maybe I had my starting node S, and we've somehow taken this long and winding path to this node B. And now we're about to add X to our known set because potentially, it is our shortest distance node in our perimeter. And so we're going to say, hey, the distance to B, which is in my known set, is 5. The distance from B to X is 3. So that results in a path 8. 8 currently looks like my shortest path, my shortest distance node. So I'm going to add it to my known set. Now, the concern here is what if there were another path to X that would result in a shorter path cost? So how can we know for certain that this other path won't exist? And the reason it can't exist was because we were deciding to choose X next. Remember, we choose which nodes we're going to add to our known set based off the shortest distance from our proposals. So if X had the shortest distance, we're about to add it to our known set, there is no node in the perimeter that has a shorter known proposed distance. In this case, in order for this path from B to A to X to actually be shorter than the path from B to X, that path from B to A has to be shorter, maybe something like 6. And so since we didn't process this A first, we know it can't exist. Our algorithm would have explored A first, then updating the path from A to X to be shorter. So there's no way for this shorter, unseen path to exist, precisely because we explored nodes in the order of their distance, their total distance. So we couldn't create, this case cannot actually happen. Let me clear my drawing before moving on. So our key intuition here is that Dijkstra's works because if we always add the closest vertices to our known sets first, then by the time a vertex is added, any possible relaxation has already happened. There's no way to have a future relaxation that would make a difference, that would actually be shorter. Now, one thing I should mention is that Dijkstra's is not always guaranteed to work on any weighted graph. For example, if you have negative weights, then this kind of claim about knowing those shortest paths kind of right away is no longer going to be true. Because with negative weights, if you were to kind of take a more expensive route early to then get a discount later, there's no clear way for Dijkstra's to know that. So Dijkstra's is only guaranteed to work without negative weights. So in this kind of same constructed example, these negative weights can really throw you off. So Dijkstra's is not guaranteed to work here because we're going to end up violating our invariant. So Dijkstra's algorithm only works on graphs with non-negative edge weights. It can potentially work in graphs with negative edge weights, but there's no guarantee that it will. So it might run through, but give you a wrong answer. So sometimes you have to be careful with if your kind of thing you're modeling might have these negative edge weights. Dijkstra's might not be the play. Oh, whoops, didn't mean to fast forward. Do not worry though. There are algorithms that can handle negative edge weights. We are not going to talk about them really in 373 because the situations that they come up in are rather limited. This algorithm to handle negative edge weights exists. It works fine, but it's just a different algorithm that we're just not going to talk about because it's not going to give us the bang for your buck that Dijkstra does. Most real world examples have these non-negative edge weights, so Dijkstra's will definitely work there. But if it's negative, you're going to have to use this other algorithm that we're not going to talk about. Now, to give you, I want to start wrapping up just because we're kind of cutting it close to time. What I want us to think about kind of where we're going to be going on Monday. We're going to be continuing our discussion of Dijkstra's. So I talked about Dijkstra's in terms of the pseudocode and examples and why it works. However, I left out quite a few details of how you actually implement this. So my pseudocode that I provided earlier is pretty hand-wavy. Like I didn't describe to you how you find that shortest, that node with the shortest distance. And one of the things we haven't talked about yet is how do we analyze the runtime of Dijkstra's algorithm? So is this an efficient algorithm? These are things we're going to pick up on Monday. Now, to give you a bit of a spoiler or a hint at what's going to be coming on Monday, we're going to need to keep track of the things in our perimeter, the things that we haven't visited yet. It'd be nice if we had some structure that could store all these nodes and give us easy access to the node that had the minimum distance, that we can add things into it kind of whenever we needed to, and that we could remove the minimum value or maybe peek at the minimum value if we wanted to. And that should hopefully kind of remind you of this thing that you can add and remove minimums from, a priority queue. So priority queues are going to be kind of the golden, the poster child of Dijkstra's. We're going to use this as kind of our core data structure to keep track of this efficiently. Additionally, one of the operations that we really need for Dijkstra's to work is this ability to update the distances, to update the priority of something, which is exactly why for project 3, we're making you implement change priority. this data structure you're writing for project 3 is kind of tailored. We kind of added that function to that priority queue interface that's not generally provided because we really need it for Dijkstra's, the ability to update the weights. So one of the kind of places that priority queues show up a lot are in algorithms like Dijkstra's and other related algorithms that process iteratively in a weighted fashion, kind of trying to find the minimum value. And so we're going to see these priority queues show up. But that's going to be a further discussion that we'll have on Monday. And that's where I kind of want to wrap up for today.